Can you see my screen?
Yes, we can see your screen and yourself. Please go ahead.
Okay. So then, yeah, start introducing my approach, which is called Game-Theoretic planning with partially ordered preferences. So, yeah, we already did a round of presentations, so you can skip this slide. As you all know, when robots leave the factory floors, things often get complicated because there are unknown scenarios, unknown intentions of other vehicles, and so on. And this is the case for autonomous vehicles that live in highly interactive and also multi-agent scenarios. And one suitable approach which can capture such interactivity naturally is game-theoretic approaches. Furthermore, the interactions are complex, and yeah, vehicles or robots often need to comply with multiple and also potentially conflicting rules and objectives. And there is also a need by regulators and the industry of transparent and interpretable systems such that accountability is possible and so on. So these 2 points speaks in favor of using alternative costs and preference structures, which I will talk about in detail later, such as lexicographic preferences and partial orders. Edmund already spoke about this, so I'll go a bit quicker here, but basically we had interactive scenarios to solve. And the fact that there are interactive scenarios is very well suited with the game theory framework. And then there were multiple and potentially conflicting objectives, such as no collisions, and at the same time road compliance, and starting in a state and ending in a goal region. So this speaks in favor of using partially ordered preferences. Just to be all on the same page and have a quick recall. In general, a game, this is a very simple game with a simple structure, is made of n players, in this case 2, where each player has a set of available actions. So in this case, each player has 2 actions, A1, A2, and B1, B2. And for each combination of actions, or what is called a joint action, we have outcome for each player, which in this case is a scalar cost, the numbers in the table. And also for each player, we can specify a preference. So we would usually specify a least preferred preference, so minimizer players for scalar costs, or a maximizer for scalar utilities. And to solve games, there are several solution concepts. So we can talk about security strategies, best response, or the most famous solution concept of a game, which is the Nash equilibria, which is a joint trajectory such that no player has an incentive to deviate unilaterally from an equilibrium strategy. So in this case, the bottom left, the outcomes from the bottom left of the table would be what is the Nash equilibrium of this game. So, but we need to define a game which is suitable for driving. So what we define here is what is called a Posetal Game, which is the result of research at the lab where I'm doing my thesis. You can find the paper on the bottom of the table, which is a game with partially ordered preferences. So instead of having scalar costs, we will have partially ordered cost structures. So again, there is a finite set of players. There is a joint decision space, which is just a Cartesian product of all the decision spaces of each player. And we have a set of metrics, which can be, for example, collision costs, fuel costs, or the tier 1 cost for the challenge, and so on. And each player specifies a preference as a partial order over the set of the metrics. Here you can see 2 examples of this. For example, the blue vehicle can, instead of specifying his preference as a single cost, he can specify his preference as a partial order. So saying, for example, that the collision cost is the most important cost for him. And then secondarily, he will be interested in keeping a clearance from other vehicles and respecting the rules of the road, because one can argue that not colliding is the most important thing. And what is interesting with partial orders is that we're not required to specify a hierarchy between all costs. We can say, for example, that here clear and rules are indifferent. So we are not specifying what is more important. And a nice theoretical result is that provided that the decision space is discrete and some additional but mild constraints on the preferences are met, this game admits a pure Nash equilibrium. So yeah, let me talk a bit more about these alternative preference structures. So commonly in the preferences game, as I mentioned, is a scalar cost. So for a scalar cost, we can compare two costs, and let's assume here we are preferring smaller costs. And then we can have, for example, in the top right, that 0 is preferred to 1, or 1 and 1 are indifferent. And comparing scalar costs with a smaller preferred cost leads to a total order. So we can rank all costs, all scalar costs on a line, as to say. But we can also consider other types of costs, such as lexicographic preferences. In these preferences, we are ranking the objectives by the most important to the least important. So here we could say collision is more important than a certain personal cost, a collision cost. And here, how we compare to costs is that we start by looking from the top and then move to lower priority objectives. So for example, on the top right, we would say that the left outcome is better than the right outcome because it has a lower collision cost. And here again, we would have an outcome which is first preferred. And on the bottom, instead, we would have indifferent outcomes. And also comparing outcomes in such a way with a lexicographic preference is a total order. So we always can rank objectives by the best to the worst outcomes. Sorry. And finally, what we're using here, which are partially ordered sets, which I already showed a bit earlier. So we are not required to specify a ranking or a priority between all couples of metrics, but we can leave some couples open. And for example, here say that rules and clearance are totally indifferent, we don't know which one is better. So in this case, the things get a bit more complicated for optimizing and so on, because we have a fourth possibility when comparing two outcomes, which is incomparability. So if we look at the top right and we compare again level by level going down, we can see that in the first case, the outcome on the right is going to be better because we have a lower collision cost. In the second case, we have indifferent costs because all the numbers are the same. And below, instead, we have the same collision cost, so we go one level below, and then we have what we call an incomparable outcome, because we haven't specified if clearance is more important than rules or vice versa. But this, however, the structure has a lot of advantages. So it allows us to have a clear hierarchy of objectives, but at the same time to not overspecify. So you can clearly prioritize what is better and what is least important, but at the same time, we are not required to specify when we don't know or when we don't want to specify. And this is very useful when we have multiple and potentially conflicting rules or objectives to consider. Furthermore, using a decision problem with such costs leads to having more interpretable systems, because it is easier to understand exactly why an outcome was preferred to another outcome. So now, yeah, the theory is there. Let's move on to the details of the algorithm. So our algorithm formulates the decision making as a Posetal game. He implements it as a receding horizon controller, and at every decision time step, and the trajectory until the next decision time step is decided. And the building blocks are a route planner, determining actually what agents are interacting in that specific moment of the scenario, a trajectory generator to generate actions, and a trajectory selection by defining and solving the Posetal game. So for a route planner, there is already a very good route planner implemented in CommonRoad, so we just went with that one. We produce a route from a start to a goal region, and as a backend, we use the default as a detail for who's interested, which is the network X reversed. For interacting agents, because Our solving the game is quite computational intensive, so we need to limit the number of participants in the game. We cannot just select all the players in the scenario, but we just limit ourselves to the players in the surroundings. So here we just construct a rectangle around the ego and look at which players are inside, and a rectangle in front and look at which players are in front. And we have the next part of the algorithm is the trajectory generator. And the trajectory generator takes the current state of the ego vehicle or also of other vehicles and generates, and also knowing the reference path, which is calculated with the route planner, has a set of parameters such as a set of accelerations, a set of steering rates, the time step, the number of steps, and vehicle parameters such as the maximum velocity, maximum acceleration, maximum steering, and so on, from the, in this case, from the Ford Escort. So given this set of information, we compute a set of trajectories which are kinematically feasible under a single track bicycle model of the desired time length and representative of actions around the reference. So as you can see in the image, we are generating trajectories which more or less follow the reference, but give some freedom of choice. And then we come to the critical point, which is the trajectory selection point, where here we are constructing a game with given Posetal preferences and actions for all players. And we define the game, we evaluate all the metrics of all the joint trajectories, solve for a Nash equilibria using iterated best response, because again, a nice theoretical result in the paper below is that iterated best response has convergence guarantees for this game formulation. And then the ego vehicle executes its actions in the found Nash equilibria. So here it's important to mention that this entire game approach is a construction to capture interactivity, because of course we cannot control actually the other players. It's not like the others will execute the action in Nash equilibria, but we are just controlling the ego. And details of implementation are that, well, the ego has such a preference structure we are giving. So the highest priority is keeping a safety distance from the other vehicles and being road compliant. The feasibility is already encoded in the trajectory generator. And then as a secondary objectives, we are minimizing the tier 1 cost and the progress along the reference. Here we just take the first part of the cost without the safety distance and the velocity violation, because the velocity violation and the safety distance are already in the trajectory generator and here as a higher level priority. And for the other players, we just assume that their preference structure is this tier 1 cost. And here we have a bit of a computational limitation, because especially the metric computation takes a lot of resources. So, and there is a joint action explosion in the sense that the number of joint actions is equal to the number, to the multiplication of the number of actions for each agent. So here we did a simplification, and for all the non-ego players, we just assumed one action. So a constant velocity and constant steering. So here we can see an animation of the algorithm in action. So you will see on the top left of the slide a video of the car moving, and in the rest of the slides it will appear the decision-making step and all the costs involved. So we can see at the first time step here, we generate a set of trajectories for the ego and one trajectory for all interacting vehicles, so the red ones. And then the vehicle moves in its lane. Here we have another decision-making step to generate a set of trajectories, and the costs on the right are the one ready for the found Nash equilibrium. If you can see it, we have a trajectory which is more dark green, and that is the selected Nash equilibrium trajectory. And here we will successfully change the lane after. Yes, so this is actually it regarding the algorithm, but maybe it's worth making a small discussion about the pros and cons of this approach. So it actually, as Edmund already said, solved 71 scenarios, and which was quite a high number. And most of the failing scenarios was because the final goal region wasn't reached, and there were less than 20 collisions. So regarding collisions, it was quite robust. One thing to say is that the scenarios of this competition is not the setting where this approach performs the best, because this approach was especially designed for situations in which there are strong trade-offs, such as unavoidable collisions or reckless other drivers. For example, from a related paper on the right, we can see an example where on the top we have a preference structure where the most important thing is to not collide. So in this case, what would happen is that the car would just choose to swerve and take trajectory B. But if we include that there are no collisions at fault, which is more important than collisions, and there is a vehicle in the other lane, then in this case, the car would choose to collide. So this is what I was talking about before with interpretability and so on. So this is more of the kind of decision-making settings which are highly suitable for our method and maybe are not that common in this kind of scenarios. And also, since the preference structures with multiple objectives is used, the tier 1 cost minimization is not the top priority. And again, yeah, there is this joint trajectory explosion problem. So we just consider a limited number of trajectories, both for the ego and for the other vehicles. And a possible idea could be to activate such a game-theoretic planner only in highly interactive parts of the motion planning, and elsewhere use another type of plan. Yeah, with this, I'm at the end of the presentation, and I'm very happy if we have a discussion run. And if you have other questions after the presentation, you can reach me at this email address. Thank you for your attention.
Yeah, so thank you very much for the presentation. I think we can ask questions, or either the in-person questions or also the other audiences over internet can also ask. So I will start. I have one question. So you mentioned there's this explosion problem with several agents, but you also mentioned that you only assume one action for the agent. So does that mean in your case you can actually consider many more agents, because you don't do that if there's no explosion, in the sense that you consider all possible actions for all vehicles anyways?
Yes, actually, by considering just one action of the other agents, then you could actually also consider a lot of more agents, because it wouldn't matter in the number of joint actions anymore. But we experimented with several combinations, so increasing the number of actions for the ego vehicle such that it has more choice, or keeping less actions and giving more choice to the others, or decreasing the size of these rectangles to determine how many vehicles are interacting. And in the end, we found that it was best to just consider some neighboring vehicles, so up to 3 to 4, and with this assumption of constant velocity and constant steering rate, we were getting the best evaluation results on the server.
Cool. Maybe just one follow-up question. So here you said you use this constant velocity and constant acceleration. So let's say if we have a more realistic model that predicts the behavior, so how different will the algorithm behave? Or because I mean, basically how good, or what's the impact of the prediction on your algorithm?
Yeah, so the impact, on the picture. Yes, for example here, so the impact of the prediction is that, for example, here you can see the other vehicles have this constant velocity and constant steering trajectories in red, and we have a set of trajectories. So if, for example, here the others have a straight line, so here the node green trajectory is actually intersecting any red line. So the metric evaluation for the collision cost would always be 0. But if instead we would have, are you seeing my mouse or?
Yes.
Okay, good. But if instead we would have, for example, here a more realistic trajectory, which is because we predict this vehicle is going to merge here, and this trajectory is going to intersect our trajectories. Of course, we can make a better decision to, for example, slow down, because there is going to be an incoming potential collision, while in this case, this is not captured because all these are not intersecting our trajectories.
Okay, thank you. Yeah.
Yeah, I also have a question. Thanks for your presentation. My question was like, how do you decide like the order of the rule book? So like in your slide 6, you show us the order, but in your slide 10, you have another order. So what's the final order for your rule book?
Yes, yeah, these were just examples, and the final order was this one. For the final submission, we tested several again, and in the end, we found this to yield good submission results in the server. So yeah, of course, our only feedback was the number of submitted, like the scoring on the server in this challenge. So we also adapted a bit on that, and yeah, I tried locally with a lot of scenarios also, but in the end, yeah, that were not the actual scenarios. So this was the final one, where the safety distance and the road compliance are the most important metrics. So safety distance is the same as described in the challenge, so part of the extended tier 1 cost. Road compliance is just a Boolean where you have a 0 if you're road compliant and 1 if you're not. And then we have the tier 1 cost and also a cost penalizing trajectories which are not progressing enough towards the goal.
Okay, so like you mentioned, like for rule compliance, you only have one or 0, but I think also you probably also the author of the rule book, like I think there was one called violation score, like to measure like how bad or how well like this certified or violated. So why is not included here for that, like the compliance for, you know what I mean? Like for example, if you violate the rule and then you have like the violation score for the rule, it's like, for example, for the rule book, so probably it's more quantitative and you can get a better result. Yeah, maybe it's just suggestion.
Sorry, which rule were you talking about now?
I think there was a paper also like for the rule book, people define like the violation score for each sub rules.
Yes, this actually all these rules. So the road compliance is defined as a violation. So it's 1 if you're not road compliant and 0 if you are road compliant. The progress is also defined as a violation. So if the progress is under a certain threshold, so you basically do progress minimum minus a minimum progress, and therefore what remains is a violation of the minimum. And we did that for the safety distance as well. For the tier 1 cost, not, because yeah, it was more difficult to define what a violation of the tier 1 cost is.
Okay, thank you very much.
So you said that you would like to see some more scenarios where you have a dilemma, or where it's really critical. Do you have some of these scenarios that you would provide for the next competition, or is this just the thing you would like to have and we should try to provide it for the next year?
No, I don't have actually any scenarios. I just know we trained not on CommonRoad scenarios, but in previous work, there was like scenarios like, I don't know, with 4 cars and an intersection, and you had to decide which one goes first and stuff like that. And there, this approach proved to be worked very well. Well, I believe in many scenarios, yeah, this kind of situations were not that common. So yeah, but I don't have any.
Was it a public data set, or was it from Emilio's from Newtonomy, or was it like, I don't know. I mean, if it's public, we can try to integrate some of these scenarios. Intersection data set you mentioned.
No, I think it was just like wait, let me think where I saw that. I think it was just results of the latest papers. Yeah, actually, I'm in Emilio's Fazzoli's group doing my thesis, as you mentioned, and I think there was the situation where these papers I mentioned, this one and the other one were evaluated.
But that's not a public data set, right? Or is it a public? Because if it's public, we could integrate it.
No, it's some CommonRoad scenarios, but it's just like handcrafted situations, just like intersections starting, because We have in our lab, we have defined like a simulator for a situation which bases on CommonRoad scenarios. So basically, you can define agents, agents with a policy, and then there is a simulation context, and you give initial positions and so on for every player. So it's like building on CommonRoad, but it's mainly for in-house testing. It's not something like open source.
If you want to get it out of your house, so to speak,
Okay.
you can just give it to us. The other thing is like, because you also from a university, did you ever give CommonRoad to students, or is it part of a lab course or something like that? And if so, can you give us some feedback? What should be improved? Just because, now you're in the call, I can just quickly ask you.
Okay, no, actually, so I'm doing my master thesis, and the first time I saw the CommonRoad scenarios was during my thesis. So it's not been any courses or stuff like that. But
do a PhD of then, or
yes,
I don't know. Yeah, okay. You're now doing your PhD.
I will talk with my supervisors in the Emilio's group, PhD students, and I will also, because they have a course on driving, of course, since they're in Emilio's group. I will talk about them about this, about integrating CommonRoad, maybe in some kind of challenge or something like that. And also, I will ask them about the simulator we have, if we're gonna make it public.
Yeah. And say hello to Emilio and Florian.
Of course, I will.
Okay. Yeah, so thank you very much for the nice presentation. I think we can move on to the next presenter. So Tinkei, you can share a screen, and then we'll be happy to listen to your presentation.
We just asked whether it can be recorded, since we keep recording.
Yes,
so.
we can
Also,
continue.
let us know if it's fine if we keep on recording.
Yep, it is fine.
Okay, please go ahead. And I think, Leon, you should turn off your recording. Sorry, your screen sharing.
Yes.
Sorry about that.
It's okay.
I am confused. Are you seeing my screen?
Yeah.
Yes.
Great. So this is one of the crazy scenarios that my solution has generated.
It's like floating on the air. Okay.
Yep.
Yeah.
So great. So welcome to my talk on sharing my approach on solving these CommonRoad scenarios. Yeah, I can skip the introduction about myself and talk a bit about how it works. So the CommonRoad scenarios, they are in an XML files. So you can, so from my point of view, I consider them to be part, half of them is like this, the environment, and the half is the planning problem. So the environment contains the lanes, which is separated into smaller lanes, and there are some interactions and some obstacles or dynamic obstacles that are the other cars. And then for the planning problem, we have the initial show state and the goal state where my vehicle wants to arrive at. So there's some criteria for the goal. For it can be like a certain time you have to reach a goal or have to survive after a certain time, and it can be position or you have to achieve certain position, velocity, or orientation. And so how I started to do this competition is that I look at the tutorials, and I have identified like 3 different approaches. And so the first one is a constraint optimization. So you consider the motion planning as a convex optimization problem. You add constraints like the other vehicles, the boundaries of the road, and your vehicle's own kinematic model, and also the vehicle model. So basically how your own vehicle transition between different states. And then you minimize a cost function. But that is kind of complicated, and it is just like the first tutorial in the tutorial page. And then thereafter, you can also use some search algorithms to do this. So in the CommonRoad search package, there are many search algorithms that are already implemented. So from the basics like the breadth first search, depth first search, depth limited search, and you also get from the class of best first search like the uniform cost search, the greedy search, and also the A-star search. And in the end, there is also this reinforcement learning that we've already seen. So it uses an OpenAI gene for the scenario environment, and then stable baseline for the reinforcement learning algorithm, which is another Python package for reinforcement learning. So these are some of the CommonRoad package that I have used, but in the end, yep, of the many approaches, I've chosen the CommonRoad search. I actually requested the high D data set, so it's like 8 gigabytes of traffic data, but then I kind of couldn't make reinforcement learning converge in a way, so I just didn't use it. And first, to convert the motion planning to a search problem, you need the different states of the vehicle to make the search. So we have these motion primitive things that kind of discretizes the problem, and we sample short trajectories that are, so every time step in this CommonRoad simulation, if you can call it that way, so it is like 0.1 seconds, and in this motion primitive that is also provided by the CommonRoad library, and we concatenate and samples short trajectories over 5 time steps, so it's half a second. Actually, I find it weird that this is like only part of a tutorial and not in the main code base, because this is kind of something important to have the search algorithms arriving at solutions. And regarding this, I made some changes to the code that eventually I decided not to use, because for the purpose of competition, I wanted it to be safe that it works in the evaluation server, but not some untested changes. I mean, it's tested for static cases, but not so much for interactive ones. So the first thing that I noticed is that my solutions, it tends to turn a lot. So even in a straight line of something with some road with a small angle, it will always it's not oversteer, but like it turned too much and then it has to compensate. So I think the problem is that the motion primitives have the step size of the motion primitive is too large, so it cannot make minor adjustments. So I kind of add a square to the spacing of how the steering angle is sampled to make smaller angle adjustments possible without increasing the branching factors too much. And then similarly for the velocity, I also do something like this. And this time it is to enable the motion primitive to reach a higher maximum velocity in a shorter period of time. And also like I kind of flip the velocity thing to let it go in reverse gear somehow. I don't know when it will be needed, but normal cars can do that, so why not just implement it? And I think we've also mentioned that there's this high-level path planner that can give a candidate path for the vehicle. So what I did with this path is that I in the heuristic function in A-star search, I give some penalty if my vehicle drives outside this path, but it is not it's not banned, so it can still deviate from this course, but it's just get a small penalty if it deviates. So as maybe I've already mentioned, eventually I chose the A-star search algorithm. So this is kind of standard in these motion planning problems, I would say. So there is this cost function that is evaluated at a certain node, or basically the current position that the search algorithm is at. And it is the sum of the true cost from the starting point to the current position, plus a heuristic cost that goes from the current position to the goal. So this heuristic function, it has to underestimate the true cost to be admissible. So basically to guarantee that the solution found is optimal. But in my implementation, I did not bound this edge. And I also consider some past behavior in my heuristic function. So for example, in the cost function, we have this acceleration and jerk, but I also have these kind of things implemented in the heuristic as well that account for previous behaviors. It is not correct in this case, technically, but it still works. I will explain, I will guess why after in the end, but yeah. And then also in the final submission, the true cost function, previously it was the TR1 cost function, but in the submission, we also include something like the safe distance from obstacles, and the vehicle has to obey the speed limit. It is not implemented, but I have something similar implemented in the heuristic function that that evaluates the distance from obstacles and also obey the speed limit. But why, like, it is totally wrong, and I will definitely fail an exam if this is an exam. But why it works because this is just a sum. So the terms that are in the heuristic function, even though they are not supposed to be there, it is just a sum, so it can just cross over to the other side in the server evaluation. So this kind of speed limits and safe distance can be transferred to the other side. It doesn't really matter because it is just a sum. And these are some of the terms I have considered for my heuristic functions. I think this normalized Euclidean straight line distance to the goal is kind of always used as an example to demonstrate something that is an admissible heuristic function, because this is always smaller than the actual distance, and it guides the optimization to the goal. But like in the cost function, there's actually no distance. This is not part of the cost function. So this is actually wrong to be here, but I also use this for to guide the other optimization goals. For example, like you want your vehicle to match the orientation of the goal or the velocity of the goal, but you don't want this cost to kick in at the beginning of the simulation. So by having this distance as a measure, I can like switch on these different costs depending on how close my vehicle is to the destination. There's also like a small part that I've also implemented that my vehicle shouldn't drive in the opposite lane. That is totally unsafe behavior. But because like the solution tracker doesn't check for this, so I just disable this cost. I've also made some other improvements. So if a path has very expensive costs, it will be put at the bottom of the priority queue and almost never evaluated, but it will still occupy some memory in the priority queue. So what I did is I just don't add it and hope that there is no visited queue that is part of the implementation. But it works. It can actually it keeps my memory consumption really low for a long time. So I just prune the nodes. And also in the current implementation in CommonRoad search, the distance to the obstacles is computed from the center point of the obstacle. But so if it is a square or a rectangle, I will pick the closest point from the vertices so that I get a more accurate measure. To be most accurate, I should do some binding boxes and collision checks, but that is probably more expensive. And there's another point is that the evaluation of the distance to obstacles that is provided in CommonRoad search, it only considers the current linknet. So if there is an obstacle that is directly in front on the same lane, but it is a different linknet, it doesn't look at it. So maybe I have to do some connectivity checks of different linklets to include that, but I didn't make this change in my final submission. And also like in intersections, there can be different vehicles from a different linklet that is not on the same linklet, but they physically overlap. So I have to look also at vehicles from other lanes and take that into account. Regarding the motion primitives, I assume that it's also part of the cost function that we don't want any sudden movement. So I always assume that we want a small state transition. So every step I will sort the motion primitives again so that they will put the motion primitive that is closest to the current state to be the next branch to be explored in the search algorithm. And also, yeah, so I just try catch everything just in case I miss some bugs. And up till now, so all the optimizations I've mentioned, they are for the static scenario. So the traffic pre-recorded. And in phase 2 of the competition, as we all know that all the scenarios are interactive, and I didn't have the time, and I was thinking of giving up. And then I realized that, so in an interactive scenario, the other cars will avoid you. So I just plan the motion as if it is in a static scenario. So I just plan a path at the very beginning, and I just follow the same path regardless of how the other traffic participants behave. And that is what I did in my final submission. Although I actually implemented that I can create some intermediate goals because we have this route planner that is somewhat high level. We can create some intermediate goals for the vehicle to follow, or we can do a full ASA search, like every n steps of the simulation, we do another search and react to the other traffic participants. But it's working kind of poorly. So it may be that I specify the intermediate goals come somewhat incorrectly, or the trajectories are not concatenated correctly so that the solutions becomes invalid. Or maybe like, if I reevaluate my ASA search in the middle of the simulations, some of the paths may be temporarily blocked by other cars. And so it cannot arrive at a solution. And so the algorithm got stuck and couldn't reach wouldn't get many solutions. So in the future, because I mentioned that I did like deep learning stuff, so I would like the A-star search to be like differentiable, so we can learn the weights with the heuristic, or just simply replace it with a whole neural network, so that as long as the search is differentiable, then we can backpropagate through everything and learn the stuff. Yeah, because when I look into the implementation of the reinforcement learning, it kind of has to learn a lot of things. So basically, learn to react to the environment. It has to plan the route itself. But if we only like turn a part of the search algorithm into a neural network, then it doesn't have to learn so many things. So it might be better in that way. And also, like, we have a solution checker, and this solution checker is basically the combination of many Boolean tests. So it tests for trajectory feasibility, it tests for like collisions and so on. And each of them so you can get a a learning signal from the deep learning, not only at the end of the simulation, but at intermediate steps, you can already get some learning signals from these validation functions. And also, like, while we really need this motion primitive to make the search tractable, because like if we branch out every single step, it will take too much computational power. But it is also the cause of some problems that I've encountered. For example, like my trajectory tend to swerve. So in the reinforcement learning approach, it doesn't really have a motion primitive. So it's better in this case. Yeah, so that summarizes my experience in doing this competition. Thank you.
So thank you for the presentation. I have one question regarding the costs. So you mentioned you considered like, I think a dozen or more than dozens of costs. So how did you tune the weights for those costs? Or how did you decide? Yeah. Because there are so many items here.
So for some of the costs, that are that are correlated with the cost function that we are using, I set them at the same ratio as the weights of the cost function TR1. And for the others, I try to normalize them in a way so that they are of the same magnitude. So it is kind of experimental. I just print the cost out and then I look at the number and then I scale it manually. But there is no special optimization technique that is employed.
So in theory, your method could be even better.
Yep.
Okay. Yeah, thank you. Do you have other questions?
So if I understand well, you replan at do you plan once at the beginning for the scenario, for the static scenario at least, and then execute, or do you replan at fixed frequency, for example? So you rerun the A star from your local your new position.
Yes, so this is where I did it, but for the submission, I did not enable this one. So I only evaluate the A star once at the very beginning, and that's it. I just follow the path and let the other cars to avoid me.
Okay, so in like real life scenario, you couldn't embed that on a vehicle.
So I think in real life it would work, but you get a lot of horns, right? I mean,
Yes,
like, because people like the thing is like, the Sumo simulator, as you said, assumes that the people are always attentive, right? In reality, people are like not paying so much attention, and we are, as said, we are planning to also add more advanced simulators, but that's not yet supported.
I guess my question was more about replanning capabilities. How do you see this solution being able to replan at, I would say, not high frequency, but frequency that is good enough for actual driving?
So in my case, it is like slower than real time. So I wouldn't run a full A-star search for the replanning, but would rather do the other approach. So I create intermediate goals to further segment so that the search goals can be concluded sooner, and less branching basically.
Because I know of maybe you know also of an algorithm that is D star, which is a dynamic A star, and you plan from the goal to your position, and once your position change, you actually have to find the robot actually. So you don't have to replan the whole thing just locally.
Yeah.
So
That's
Anytime algorithm. Yeah, these stars in anytime algorithm.
Yeah, there's anytime versions, not the original one, but Delight is.
So I would say that it is kind of implicitly embedded in the cost function because I have this route planner. I mean, it is obviously like completely different, but because I want my car to follow this route anyway, so my A-star search will always kind of follow this route in general. So even if I have to restart from the middle, it is somewhere along this route.
Okay, thanks.
Okay.
Yeah, I may have another question regarding the shift distance. How did you include the shift distance into heuristic? This part I didn't really understand. Could you explain this part again? Like, I think slide 6, you kind of say like the shift distance and or one earlier. I think you kind of like the speed limit and the shift distance, a heuristic.
Give me a moment.
8, yeah, probably 8. Yeah, right, this one.
So this basically the distance from the obstacles I've added. Besides using the vertices, I also added a safety margin. So I consider the object to be larger than it actually is. So when you compute the 4 vertices from the center and the length and the width, I multiply it by certain factors to make the object larger. And this is how I implemented the safety distance.
Okay, yeah, thank you. And I just wonder, like, since you want to minimize the heuristic, but want to maximize the safe distance, so there will be some conflicts if you include it into the heuristic function. So
I see.
Yeah, thank you.
Okay. So
I have a question in a completely different direction. So you said you study physics, right?
Yep.
Are you planning to continue with this somehow, or are you going in a completely different direction, or just out of curiosity what your next steps are?
Because right now what I did,
Yeah.
like right now what I did in physics is somewhat more numerical stuff. So I did, my research area is like finite element exterior calculus, but that is kind of too theoretical for me. I would just like more physics. And basically, like my goal is to apply deep learning in physics. So that's what I wanted to do. And kind of learning about these kind of things also helps in that way. So that's why I'm always interested in the introduction to deep learning courses or your course in in AI. But yeah, that's kind of the direction that I wanted to go.
Okay, thank you.
Okay, thanks.
Yeah, thank you very much for the presentation. Yeah, do we have other questions from the audience online? If no, then we will proceed to the next one. Okay, yeah, thank you for the presentation. Then our last presentations from the winners. Xiaocong, you can share a screen and we will be happy to hear your presentation.
With us recording.
And also, yeah, if you consent to the recording, if that's fine.
It's fine. Yeah, that's okay.
Okay, thank you.
Hello, everyone. I'd like to firstly appreciate the efforts that CommonRoad made to make this competition happen. We had a great journey here. And here's our planner. This is a joint work with my teammate Mingyang Cui, Yibing Yang, Lei Cao, and I am Xiaocong. I also go by Desmond. This talk will cover the following three parts. Firstly, the general framework of our planner. The whole planning process starts from information gathering and reorganization. We extracted the details about obstacles, road structure, and planning goal from the raw scenario and streamline them for the following steps. Next, state checking. As we designed two different semantic decision makers for respectively conflicting and non-conflicting scenarios, this step serves the purpose of checking potential conflicts and choosing decision makers accordingly. After semantic decision maker is selected, a conventional decision-making, planning, and executing process will be conducted, after which we update our ego cast motion for the next round. Here are some information about the state checking and the decision maker selection. The CommonRoad scenario provides a starting position and a goal region in a given roadmap, and this allows us to firstly identify possible passing by region as shown in the green shadow. Then we divide this region according to whether the central line have crossing points, marking the crossed region as a conflicted region and the remaining parts non-conflict region. In conflict regions, we firstly convert surrounding roadmap into a two-dimensional grid map, and then generate action sequence with MCTS, Monte Carlo tree search. And this process will be detailed later. In the conflicting region, we are concerned about whether our ego car should yield or rush, and we also use a game-theoretic model to make decisions in these cases. Speaking of which, thanks a lot for the very good recall of game theory from Leon, as our planner is partially game-theoretic. And then I will give some technical details about this planner. Firstly, the MCTS. MCTS is applied for semantic decision-making in non-conflicting scenarios. It employs global information extracted from CR scenario, including the map, the target, the obstacle, and generate optimal action sequence. The lower figure shows our basic idea of building the decision tree. A state includes the motion of all vehicles, and the collection of ego cast feasible actions could bring the old state to a new one based on our predefined transition model. And this process is for both ego vehicle and surrounding other vehicles. All the policies should reach the target, and the best policy will be selected based on a cost function that we find. The state transition of the surrounding other vehicles include two maneuvers: constant speed or car following. The master distance-based switching logic is designed for this AEB-like function. And for our ego car, we designed 3 longitudinal actions: acceleration, deceleration, and constant speed, and 2 lateral actions, left or right merging. And the gap searching logic is also designed for the merging. Every action on the decision tree should be feasible. Our feasible checker considers collision avoidance, drivable area, reaching target, etc. Then the game-theoretic interaction planner is used to tackle conflicting scenarios. This is also the new feature in this year's planner. We would like to take the unprotected left turn scenario as an example to roll out the planning process. The individual reward are designed to encourage ego car to pursue driving progress and avoid lane deviation. And the group reward is set to ensure safety, though we didn't set any hard constraint for collision avoidance. The individual and group rewards together comprise a utility function, and we assume the interacting vehicle shares the same reward terms, but could differ in the weights. Here, weights in the utility function decides whether a vehicle focuses more on ego reward or group reward. We use the trigonometric value of an ego phi to govern the weight vector. As such, different value of phi means different social preference of a vehicle. And this phi was named interaction preference value, IPV. By setting
just a quick comment, like in the previous approach, it would have been fully egocentric, right?
Mm-hmm.
Right?
Yeah. By setting a
in your case, it's like in your case you didn't drive fully egocentric like in the previous approach, where you just drive and the others will take care of the rest, right? So that would.
This help. Yeah. This we don't drive quite self-interested, because we actually this process help us better predict the action of other vehicles, as they may not also be self-interested.
Thanks.
So during the planning process, by setting a specific IPV to a virtual background vehicle, we could solve the game and predict the involvement. And we could conduct multi-process in parallel to get different results under different settings of IPV. And then we continuously compare the actual trajectory conducted by the background vehicle and those from the virtual candidates to identify the IPV of the actual background vehicle. This follows intuition that the more similarity in IPV, the larger possibility to yield the same trajectory. And this process is supposed to run online, but we simplified it to avoid expensive computation. As you may have noticed, the GT-based planner is also applicable for human-involved interaction. And this is actually an idea from a project that deals with human driver interaction. We analyzed the IPV of human drivers, and the background vehicles in CommonRoad are generally at this position. They're quite cooperative and nice guys. And we eventually find that the best way to interacting with those cooperative guys is actually being aggressive. So during the parameter tuning process, our planner is actually a bit competitive. And with this prior knowledge, we don't have to estimate the IPV of interacting agents online, as we have known they are cooperative. So if you are interested in this idea, here are some reference for you. Finally, the Lattice Planner provides a trajectory based on the target region given by the semantic planner. The Lattice Planner we used is generally a classical version from Apollo, with basic steps of sampling, constraint checking, and sample selecting. Some minor modifications are made to the problem we faced. For example, as the target region of some cases are quite small, we restrict the sampling region to a small one around the target position. And during the whole process, we also used some very nice tools from CommonRoad, like the RWTH Planner. I'll give a short summary on a planner and its performance. In semantic decision making, we used MCTS for non-conflict scenarios and the GT-based interaction planner for conflict scenarios. Lattice Planner later generate trajectory solution from the semantic target. And now Planner could be implemented in real time, and it succeeded in more than half of the examples in the local test, conducting tasks including lane changing, car following, in and off the ramp, or unprotected left turn, etc. And as just Leon mentioned, game-theoretic model is not always the good thing for the planner. Sometimes it works bad in non-interactive scenarios, or in some scenarios that only a little traffic is around. Thanks. That's all for my presentation.
So again, I have a question. So comparing your method with Leon's method, so Leon there, he assumed like single action for other vehicles because he wanted to prevent the state explosion problem. But in your case, you seem to consider like more actions. So don't you also have this explosion problem, or you have other tricks to avoid that?
I also use iterative burst response to solve the game, and actually it restricts the number of interacting agents. We also select only one interacting agent, and it cannot be implemented in real time if we simultaneously solve the game with more than 2 interacting agents.
Okay.
So we also face such problems.
Yeah, so you basically also have to limit the interacting agents, and then yeah, do this. Okay, yeah, thank you very much.
Mm-hmm. Thank you.
I might also have a question. So which vehicle model do you use? Since you said you use like a lattice planner from the Apollo, but I think they didn't share the same vehicle model as the CommonRoad vehicle models.
Yes. So this eventually made some errors in our solutions because we use a simplified bicycle model in this process.
Okay. So like you use the CommonRoad vehicle model constraints, or you didn't really consider this kinematically feasible constraints?
Yeah. Yes.
Okay. Thank you.
Yeah. Do we have other questions from the audience online?
Are you planning to participate next year again? Just a very simple question, or maybe you don't know yet. But I think you win, say, okay, now I'm at the peak of my career. You know, when you win the CommonRoad competition, there can be no better success in your life, essentially. So then you could say at the peak of that you don't participate again, or what's your plan for the future? Or again, also the question, are you planning to use this also for a lab course, or let's say for homework, student homework, or like, so we use it, for instance, in our artificial intelligence class lecture as a programming exercise. Do you think that could be something for the future?
Sorry, I didn't really catch your ideas, but for my planner, our future plan includes to implementing it into the the real case, as we don't think CommonRoad, the sumo in the CommonRoad is the best choice for the game-theoretic based planner. And actually, after we adding the game-theoretic part into our whole framework, we didn't actually get further merits for the submission results.
Yeah, I mean, of course, I mean, it's like every competition has like aspects which can be improved, right? And one aspect is that the simulation, the background is, I mean, Sumo is the oldest and best known simulator, but it has been designed not for autonomous driving, but for traffic analysis, right? And as I said, we are going to improve on that in the future. So then maybe hopefully you have a bigger benefit from that. And the other question was just, I mean, we use CommonRoad also in education, right? So that we say, okay, with a group of students, let's say we have a practical course on motion planning, and that they use CommonRoad to, to learn how to program a motion planner. And I don't know if you do have any plans like that for teaching at your university.
Actually, I have mentioned to Adamant that our group also developing another website just like CommonRoad. Maybe they have, I guess they have emailed to you. Our website is named Onsite. It's a autonomous driving testing platform in China, very similar to the CommonRoad. So we are going to pay a bit more attention to developing a new Chinese style AV competition.
Okay. So that will be also open for the international public, or was it focused more on China?
The international version is currently under construction. I guess maybe next year I will bring it here.
Okay. Yeah, maybe you can next year you can present your Chinese version then. If you
All right, I'd like to. All right.
Okay.
Yeah.
Yeah, you have a question.
Yeah, I have a question, but not for the speaker, but for all the speakers. Is do you plan to release your solution as open source eventually? This is for you and also the other participants. So does anyone plan to publish the code of their trajectory planner at some point?
Okay, maybe I can go ahead. Yeah, I'm planning to do that. It's already in a GitHub repository, and we need just a quick cleanup, which I haven't been able to do because I'm working on the submission of my master thesis right now. But after that, I'd like to clean it up, and yeah.
Okay, thank you.
For me, I forked a CommonRoad repository on GitLab. So, but there is some, I don't know, because I forked a project, I cannot make it public, but it is like if you have access to the LLC GitLab, then you have access to my project as well. So it's kind of public, but not,
But for that, maybe you can also put it on GitHub. I think that's also an option.
Yep, all right.
And our planners has been published on the GitHub. But I guess as we have published in the Doc Hub, it's kind of published as you can easily get our codes from the Docker.
Yeah, but Docker is like a black box, right? It's like you don't see how it really works. It's like
I mean, you can always SSH.
But you can actually use some tools to copy the codes from the Docker and to the local.
Yeah, so I think if that's okay, maybe since you have submitted your planners with Docker, so basically we just have to announce release this Docker IDs, and then the others can have access to it. Yeah, I think that's one of the options.
That's okay, right?
Yeah, okay. Thank you very
Yeah,
much.
of course.